Welcome back to Meaning from Data, Statistics Made Clear. Today we're going to take on the statistical challenge of analyzing sports statistics, which is a sport of its own. Statistics are, first of all, extremely important in sports, particularly in making the managerial decisions. And I mean important managerial decisions, like the ones that you make when you're sitting around and at home on your couch and a bunch of people are there and you're watching some game and you're helping the person, you're helping the manager make a decision about what he or she, usually he, should do next in the game. So these are very important. But not only are they important for that really useful work, but it's also true that these sports statistics are wonderful illustrations of statistical ideas that have applications well beyond sports. So I think there's no question that looking at sports statistics issues is a wonderful way to both learn about statistics and also have some fun. So let's begin with a couple of, in this lecture we're going to pose a couple of sports questions, and the first important question that we're going to pose is the question, who was the best hitter in the history of Major League Baseball? Well, it sounds like an innocuous question. It sounds like a simple question, because it sounds as though it's a question of just saying, let's look at the measure of hitting, namely the batting average, and decide if who has the best batting average, and that is the answer. But in fact, it brings up all sorts of basic principles and basic challenges about statistics. The first one is to clarify the question. Who is the best hitter? What does that question mean? What evidence are you going to accept as supporting the contention that a particular individual was the best hitter? So the question forces us to clarify the relationship between what we measure and what quality we're trying to actually describe. And that, you see, is extremely fundamental in both statistics, certainly in statistics, in the world in general. So although we might at first think that the question really amounts to who has the best batting average, who has the highest batting average in history, we might think that's the question, but let's take that as the provisional issue and see what happens. Well, first of all, right off the bat, we have some, isn't that great? Right off the bat. Okay, right off the bat, we instantly come up to an issue about baseball averages. And that is that certain players, such as the pitcher, don't really bat well. So the batting average of a pitcher, is inconsequential, and that shouldn't be related to the thing. Of course, that pitcher's not going to win the batting championship anyway, so maybe that doesn't matter. But the first question is, what does the batting average actually measure? The batting average measures the fraction of the times that a batter comes up to the plate and the pitcher throws the balls to him and he tries to get a hit. And if he successfully hits and goes to first base, then that's a successful hit. There are lots of wrinkles to this. For example, if he makes a sacrifice fly, then that doesn't count against him. If he walks instead of gets a hit, then that doesn't count as an at-bat. And there are other wrinkles. But basically, the idea of the batting average, which, by the way, is always a decimal point and then a three-digit number. So 0.250 is a 25%, and it's called 250 in the parlance. So the point is that the batting average is telling us what fraction of the time a hitter actually gets a hit, basically speaking. Okay. So, but that is the first issue of what it is that the batting average actually measures. The second question that you want to know in trying to say who has the best batting average is, do you mean the best batting average over the entire career of the player, or do you mean the best batting average over an individual season? In a way, the best hitter, suppose that the hitter went into his dotage and had a lot of low batting average seasons at the end of his career. Well, maybe he was really the best hitter, but it was earlier in his career. So let's concentrate then on the question of a single season. So we'll say, who's the best hitter in a single season? And that's just a decision we make. The next question is, who are going to be contenders for this crown? Suppose you have a batter, and it occasionally happens that a batter will only bat one time during the season for some reason. Maybe a pitch hitter comes in, just hits one time. If that person got a hit, then that person would have a perfect batting average and would throw off the whole scale. So we have to make another decision that only players who have got quite a bit of hits during a season should be contenders for this crown. And so we'll make the arbitrary decision to say that the person had to have at least 80 at-bats to count for a contender for the crown. So with these assumptions, let's just see how we do. Looking at the batting averages of the highest batting averages in the history of baseball, and here is a chart that shows them. Here they are. The highest batting average occurred in the year 1901, and it was a batting average of 426. 426. This is an amazingly high average, by the way. And here we have a 423 in 1924, a 420 in 1922, and so on. Look at the years in which these very high batting averages took place. Look at all these years. Can you see these years? All of these years, 1901, 24, 22, 11, 12, 11, 20, 41, 25, 23, and so on. The batting averages, here's the 400 batting average of Ty Cobb in 1922. The batting averages you see are in order. And notice that all of these highest batting averages took place before the year 1942. 1941 was the last year in which any batter hit 400. Now, it's true that down here at the very bottom, we have in 1994, Tony Gwynn hit a 394 average. But all of the previous ones above that were 1941 and before. Well, when we see statistics like this, we have to ask ourselves, what's going on? Because are we saying that all of the greatest hitters in baseball all played baseball before 1941? That's not a tenable conclusion. We seek to find an explanation for why it would be that all of these high batting averages occurred so early in the century. Well, let's look at the batting averages over the years. One explanation that we might think is the explanation is that maybe in the early years, the batting averages in general over all of the players were much higher for some reason. You know, the balls were different, the fields were different, something. It may be that all of the batters had higher batting averages, and therefore it's not a fair contest. So what we can do is look at the data. These are the average batting averages. The average batting averages for every year from 1880 up to the year 2004. So these batting averages, you see that in the year 2000, the batting average was about 266. Well, notice that this seems like a sort of a complicated scatter plot, and it's all over the place. But as a matter of fact, if we look at it a little differently, if we put it on the chart that shows that where the vertical axis goes from a zero batting average to a perfect batting average, we can see that actually there isn't a great deal of difference between the years. And if we look carefully at our chart, we'll see that in fact, in the year 1920, the batting average was within 2 points of the batting average of the year 2000. So that, yes, there are differences, particularly like this year was a very high year, but a very early year before 1900. And even these years in the about late 20s had very high years. So that the average batting averages were higher, so we might expect some people to do extremely well. In fact, though, there is an anomaly here. If we look at the years 1920 versus the year 2000, both those years had almost the same average batting average over the whole league. But look what happens. If we look at the top batting averages for 1920, George Sisler, Tris Speaker, Joe Jackson, Babe Ruth, we can see that all of these people have higher batting averages than the very highest batting average in the year 2000, even though the batting average overall was the same. Now, this is a little bit odd. Why would there be higher batting averages in 1920 versus the year 2000? It doesn't seem that our guess that maybe higher batting averages overall are accounting for that difference. So we have to think more. And here's what we do. And we've seen this before actually in several lectures. And that is that we notice that in the year 2000, the batting averages are more closely clumped to the average than they were in the year 1920. In the year 1920, they were more spread out. The standard deviation in 1920 was greater than the standard deviation of the batting averages in the year 2000. Well, that gives us an idea about how we could compare batters from eras where there are two different standard deviations. Instead of just talking about their absolute batting average, we could talk about how many standard deviations above the mean the batters were from one year to the next. And in fact, by doing that, we could give everybody a measure. Instead of saying that Joe Jackson has a batting average of 382, we could say how many standard deviations above the mean of his year, 1920, was his batting average. In his case, it was 2.36 standard deviations above the mean. Moishisa Olu had a batting average of 355. You see, that's a lower number. 355 is lower than 382. And yet, because the batting averages overall were more compressed, his batting average was also 2.3 standard deviations above the mean. So comparing batting averages on the basis of their relative standing, relative to their contemporary players, seems like a good way to measure quality of a player. Now, look what's happened over the century. These data here represent the standard deviations of the batting averages for every year from, well, way back here up to the year 2000 and beyond. The standard deviations are clearly declining over the century. You see that? And these are for batters who batted at least 80 times. You can see that the standard deviation in the year 2000 was much less. We might ask why the standard deviations are lower in later years. Stephen Jay Gould argues that batters, and in fact pitchers and fielders as well, have all moved closer to absolute human limits of perfection. As professional players use techniques and get closer to that limit, their variation in performance must decline, and therefore the standard deviations decline. Well, what that means is it gives us an opportunity to evaluate the quality of a batter relative to his contemporaries across the era, across the span of time. And in that measure, we can say for every batter, how many standard deviations above the mean was that batter? And we can take all of the batters in history and look at their standard deviations above the mean for that particular year, for every year, and here's what we get. In this measure of standard deviations above the mean batting average for that year, we see that the winner would be Tip O'Neill, who, incidentally, I thought was a politician. But in 1887, Tip O'Neill had a batting average of 435, which, by the way, is amazing for anybody. And the number of standard deviations above the mean was 3.58. So that was his Z-score. Now, you may recall about standard deviations that when you have a normal curve, the number of standard deviations away from the mean tells you how much of the data lie that close to the mean. And remember that 68% of the data lie within one standard deviation of the mean, 95% of the data within two standard deviations of the mean, 99.7% of the data lie within three standard deviations of the mean. Here we have an example of a player who was 3.58 standard deviations above the mean. That corresponds to a fraction of 1 in about 5,000. That would be that far away from the mean in a normal distribution, which batting averages are, roughly speaking. So what's interesting about this way of comparing the batting prowess of people over time is that look what you have. The number one player is Tip O'Neill from 1887, whereas the number two player is Tony Gwynn of 1994, who had a batting average of 3.394, which is an amazingly high batting average for a modern era player, and a Z-score of 3.56. Then we move on to George Brett in 1980, and then back to 1884, Fred Dunlap, and then we get to Ted Williams, Rod Carew, Tris Speaker, and so on. In this evaluation, we get a different list of people from the people we got just looking at their high batting averages. And here are the next 10, which include familiar names: Ty Cobb, Ted Williams again. We have a very modern player, Ichiro Suzuki, 2004, at a very high number of standard deviations above the mean. But we must ask ourselves the basic question: are we measuring the qualities that we really want to describe as the best hitter? You see, batting average is one quality, but when you get a hit, there are several different ways you can get a hit. You can get a single, but you could get a double, a triple, or a home run. Now, you should get extra value for hitting a double or a triple or a home run than just getting a single. Well, so we could devise a statistic to measure that quality. And in fact, this is done. What we could do is give twice as much value for a double, 3 times as much for a triple, and 4 times as much for a home run. And this number is called the slugging percentage, even though, by the way, it's not a percentage. It's not a percentage because it's out of 4 instead of out of 1. The slugging percentage, if you got a home run every single time you came to bat, you'd get 4 points each time, so you'd get a total of 4. That would be perfect. But people who hit several base hits often, multiple base hits often, will have a higher slugging percentage. Well, this is a different way of deciding who is the best hitter, looking at slugging percentages. Well, we can have an interesting analysis by looking at that evaluation of hitting prowess and listing people in order of their slugging percentage. We get a different picture. So here we have number 1, Barry Bonds, slugging percentage 863. Babe Ruth in 1920, 847. So these are season by season, so the same player appears different years because we're looking at the slugging percentage for a season. So here we have Bonds, Babe Ruth, Barry Bonds, Babe Ruth, Lou Gehrig, Babe Ruth again, Rogers Hornsby, Mark McGwire, a relatively modern player, Jeff Bagwell, Barry Bonds again, Jimmy Fox, McGwire, Babe Ruth, Sammy Sosa, Ted Williams, Babe Ruth again. So Babe Ruth occurs an amazing number of times on this list of slugging percentage. Now, one wrinkle to this list, which I think is rather interesting, is Barry Bonds. Look at Barry Bonds. He has numbers here in the year 2001, 2004, 2002, and down here 2003. All the years 2001, 2, 3, and 4. He is in this list of the top 20 sluggers, slugging percentage. Now, what's really interesting about that fact is that up until Barry Bonds was 35 years old, he played professional baseball starting at age 21. From years 21 to 35, he never had a slugging percentage that reached the 700 level. Not the 700 level, not the 800 level, the 700 level. He never reached the 700 level, but in the year 2001, he got much better and had the record for all time for slugging percentage, and in fact, in 4 years. And this is a remarkable statistical accomplishment to have had in all the years from age 21 to 35 a certain level of performance, and then to have a big leap in particularly late in the career of a baseball player. Now, when we look at statistical data that presents an anomaly, an apparent anomaly, then what we tend to do is to look for a lurking variable. That is to say, something that's going on that's not apparent in the data that's being presented. Well, looking at baseball statistics, we have another kind of issue associated with who is the best hitter, and that is that if you're talking about contributions to the team, just getting hits is not the only contribution for the offense. In fact, it's very important to get a walk. If you can get on base, whether it's by a hit or by a walk, you're on base and in a position to help with the scoring. So in fact, measurements such as on-base percentage are very important, and managers will look at issues such as combinations of on-base percentage and slugging percentage and batting average and make formulas that try to assess the real quality to the contribution of the offense of a player based on these kinds of statistical evaluations. So the theme of this first exercise was then, one of the important ideas was the correspondence between what we measure and what it is we're actually trying to ascertain. Very important issue in statistics. We're now going to turn to a second issue, a sporting issue. And this is one that all of us who have actually played sports have experienced personally. And that is the idea of having a streak. A streak occurs when you're in the zone. You know, you've got that hot hand, everything you do is right, it just works, and you just feel great. So people have been trying to study the question of the hot hand. Does this, a player's on a streak, he just can't miss. But the question that we want to ask is there really such a thing as a hot hand? In other words, there are streaks. Yes, there are definitely streaks. If you have people, for example, basketball players, there are streaks where the basketball player will hit many shots in a row. But the question is, are those streaks better described by saying that that player is in the zone and has a hot hand and is actually doing much better during that time? Or, alternatively, is it like flipping a coin, where if you flip a coin, it lands heads or tails, you flip it again, heads or tails, heads or tails. It may be that you flip it sometimes, 10 times in a row, it comes up heads. You wouldn't want to say, wow, that coin really has a hot hand now. You wouldn't want to say it really has a hot hand. You would say, in fact, it's a result of the fact that if you do things randomly, you are going to sometimes get a long sequence of results that appear not to be random. See? So the question is, how are we going to tease apart these two possible descriptions of a phenomenon that is real? Namely, that yes, indeed, this basketball player does sometimes have many baskets in a row. Do we describe that better by saying it's just explained by randomness and that the player has a certain random possibility of getting making a basket or not each time, but just because of randomness alone, it turns out that this streak happened? Well, this is a very deep question. The question of distinguishing randomness from something that involves intent. So let's try to think about how we would go about comparing the random to the things that are caused for a reason. So in order to do this, let me ask you to look at the following list of H's and T's. I know this is a long list of H's and T's, but I want you to look carefully at this list, and I'm going to tell you that both of these have the same number of H's and T's, but they were created in two different ways. One of these strings of H's and T's was created by taking an actual coin, flipping the coin, and then just recording H and T according to how it came up. That's the random list. The other list was created by a person who was just asked to write down a random list of H's and T's that would come up randomly. Okay? So it's a simulation of randomness that a person did, but didn't actually flip the coin. Now, this is a wonderful question to ask. Can you tell the difference between these two lists? I mean, in a way, it seems impossible because the person intended to try to make it random, and they sure look random. Don't they look random here? These all look random. These look random. But as a matter of fact, looking at those lists, you can be very, very confident that the second list here is not created by a random process. And the reason that you can be so confident that this second list is not from a random process is that it does not have streaks. Streaks are rare events, but they're absolutely expected if you have a long sequence. You see what I mean? You have to expect the unexpected. You have to expect the rare. That's one of the properties of randomness, that a certain number of times you will get a long streak of 6 or 7 in a row. Look up here. This was created by flipping coins, and look at this. Here you have 6 H's in a row. Often a person who's actually doing, intentionally writing down what he or she is told to make appear random would think, oh, you know, if I put 6 H's in a row, that doesn't seem very random to me. You see? So that you can actually tell the difference between random and apparent and trying to be random by looking at that kind of distinction. Well, what this is saying is that you expect streaks to occur by random chance alone. Let's look at how we would then go about trying to analyze streaks in basketball. So here we have a series of 63 hits and misses that a player did in a basketball game, and the question is, can we try to evaluate from looking at that streak whether or not it's the result of randomness or whether he was, whether it's an indication that there are streaks? How would you go about distinguishing the two? Well, here's an idea. Suppose that a person who made a shot was more apt to make another shot because, you see, they were in the zone. You see, that's what a streak really means, is that somehow making one helps you to be better at making another. So what we could do is we could say, let's look at how often the person successfully made the basket after making a previous basket compared to how many times the person made a basket after a previous miss. You see? So hit means that it was a good basket. M means it was a miss. So what we can do is look at this. After a hit, how many times was it a hit? 16. After a hit, how many times was it a miss? 12. So after a hit, there were a total of 28 occurrences, of which 16 times it was a hit, 12 times it was a miss. After a miss, on the other hand, there were 13 occurrences where this player got a hit, and 21 times when it was a miss. So this gives us the same kind of a square of data that we saw earlier in the lecture about the law when we were talking about the discrimination case. The question here is your probability of getting a hit after a hit different from your probability of getting a hit after a miss, or is it about the same? When we actually do the analysis, we can see that there's always going to be some probability involved in saying how often you're going to get hits and misses. There'll be some distribution. If it's just random, you would expect the same proportions of hits and misses after a hit as the proportion of hits and misses after a miss. But you'd also expect a certain amount of variety just randomly. Well, this once again, the chi-square statistic is the method by which we compute how rare the disparity after hits and misses is in this data, and we see that the p-value for this is 0.14. And generally the p-value, in order to have it be persuasive as a measure that something happened not by chance alone, we would require that the p-value, which is the probability of something that rare or rarer occurring, to be less than 5%. So since this is 14%, we would not reject the null hypothesis that in fact you have that having a hit or a miss does not affect the frequency with which you then get a hit or a miss on the next on the next opportunity. Well, these issues that we've looked at have brought up lots of basic statistical questions. One is asking the right questions, and using what data to evaluate and support evidence for answering a particular question that you're interested in. And then the second question about the hot hand brought up the very fundamental question about nature, namely about the meaning and the measure of randomness. I'll look forward to seeing you next time.